Hello and welcome to my talk about Russian natural language generation, creation of a language modeling dataset, and evaluation with modern neural architectures. My name is Zein Shaheen. I am a PhD student at ITMO University, and this is a joint research with my supervisor, Dr. Gerhard Wohlgenannt, Basil Zaiti, Dr. Dmitry Mormetsev, and Dr. Vadim Pak from St. Petersburg Polytechnical University. My agenda for today, I will start by describing the motivations behind this work. Then I will go through a brief description of neural networks for text generation. Then I will describe our method for dataset creation, results and evaluation, and finally conclusion, discussion, and let us start with motivation. Text generation is a key component in many systems that produce text, such as translation systems, dialogue systems. These systems should produce texts that are grammatically correct, well-formed, without mistakes, and these texts should be syntactically correct as well. Most researchers in this field of study experiment with English. However, in this research, we wanted to experiment with another language, which is Russian language, which is rather richer than English. To achieve that, we needed the dataset. However, there is no standard dataset for this task in Russian language, so we decided to start this research by preparing a dataset for Russian language, which is could be considered as a reference for later researchers. Recent advances in the field of NLP have brought us transformer-based models which achieve state-of-art in many domains and tasks, including natural language generating. Although these models are able to generate texts which are well-formed, however, these models come at a large scale and they cannot be deployed to mobile phone. For example, they need quite large resources, and they are not suitable for tasks such as dialogue system, which run in real time. We decided to experiment with models that work at a small scale. We created a dataset of short sentences, and we performed an evaluation, including different methods of evaluation, including perplexity, statistical study, and expert evaluation. Now, let us talk a little bit more about neural networks for text generation that we used in these experiments. First, I will explain the difference between standard autoencoder and variational autoencoder. Standard autoencoder consists of an encoder and a decoder. The encoder encodes the input X into a code Z in the latent space, and the decoder uses Z to decode an output. So the encoder calculates the probability distribution of the latent code Z given the input X, where phi is the parameters of the encoder, and the decoder calculates the probability distribution of the output given the latent code, where theta is the parameters of the decoder. The standard autoencoder is trained to reconstruct the input X at the output of the decoder, and a commonly used loss function is the negative log likelihood, which we try to minimize. A variational autoencoder instead encodes the input X into a region in the latent space, and this region is defined using Gaussian distribution, and the parameters of this Gaussian distribution is the mu vector and the diagonal covariance matrix sigma. First, Z is sampled from this distribution using mu and sigma, and then it is used to decode the output. The objective of variational autoencoder is to maximize the lower bound, which consists of two terms. The first term is the reconstruction loss, and the second term is the KL divergence between the probability distribution of Z given X and the prior. The prior is usually selected as a standard Gaussian. We can notice that KL divergence term is multiplied by a weight beta, and if we set beta to 0, we can see that the objective of variational autoencoder will be the same as the objective of a standard autoencoder. We compare between different strategies for selecting beta. The first one is to keep it as 0. Second one is to set beta to 1. Third one is the monotonic annealing. We set beta to 0, and then in the following iterations we increase the value of beta gradually to 1. Then we set beta to 1 for the rest of the training. The cyclical annealing, we split the training into cycles, and for each cycle we follow the monotonic annealing approach. Our second chosen network is the sequence GAN. Basically, GAN or generative adversarial network consists of two networks, the generator and the discriminator. The discriminator distinguishes between real and fake data, whereas the generator tries to generate data that looks real. Therefore, it tries to fool the discriminator. Although GAN has been applied to many tasks in computer vision successfully, it is not trivial to apply GAN for text generation. The reason behind this is that texts are discrete, has a discrete nature, and we will need the argmax function to sample a token at each time step for sequence models. Argmax functions are non-differentiable, so we cannot easily pass the gradients from the discriminator to the generator. The second reason behind this is that we cannot get an evaluation score for a partially generated sequence, because the score for the partially generated sequence depends on the score of the complete sentence. You and others adapted reinforcement learning with GAN for text generation. They use reinforcement algorithm, so they treated the generator as an agent, and the action is the next token to be generated. To get a reward at a time step, they needed to generate the completion of the sentence, so they use Markov chain Monte Carlo to approximate the reward at this time step by generating several sessions. In our work, we first pre-train RNN language model and use sequence GAN to improve the samples of this language model. Now we will look at how we created the dataset. We used a well-known dataset in Russian language, which is length and use dataset. It contains about 800,000 articles from news. We pre-processed the texts in this dataset by lowercasing the text, replacing URLs with special tokens, separating punctuations, replacing digits with special character D, and this will allow us to capture meaningful meanings for numerical tokens such as D or 3Ds or 4Ds and so on. Before pre-processing, we applied sentence tokenization, and after pre-processing, we kept the most frequent 15,000 tokens as vocabulary, and we represented out of vocabulary tokens using UNK token. To create the dataset, we sampled sentences for training, development, and test sets from the previously preprocessed sentences. We chose 200,000 for training, 16,000 for development and test sets. And we accepted only sentences that fulfill the conditions. Sentences with less than 40 tokens doesn't include English words, have even number of quotations, and they are balanced according to brackets, and it contains less than 10% unknown tokens. Here are the statistics for each split of the dataset. We show a number of examples, mean and standard deviation, and the number of unique tokens. Now we will show results and evaluation. First, we calculated the perplexity for each of our models on the test set. We can notice that for variational autoencoder, the zero schedule gives the lowest perplexity. The next best perplexity on test set is for cyclical annealing. RNN language model and sequence GAN show much higher perplexity on test set. For the statistical evaluation, we sampled 10,000 texts using each model, and we extracted the statistics from these texts. We compared the statistics of these samples with the statistics of the test set. In terms of uniqueness, except for the constant schedule, all the models generate diverse samples. However, the constant model generates only 231 samples, unique samples. The zero schedule of variational autoencoder RNN language model, sequence GAN, generate samples that don't overlap with training set. However, the other schedules of variational autoencoder have a little bit overlap with training set. In contrast to variational autoencoder, RNN language model and sequence GAN show statistics that are close to those in test set in terms of mean number of tokens per sample, standard deviation, and the number of unique words. For a better evaluation of the models, a native Russian speaker evaluated samples of each model, and the table shows how many correct sentences out of 100 for each model. A sentence is considered as a mistaken sentence if it contains at least one grammatical mistake. So the table shows that cyclical and linear annealing of variational autoencoder show the best models in terms of grammatically correctness, And it is surprising that RNN language model and sequence GAN show too many mistakes. We projected latent codes of the sentences in the development set for each method on 2D space using TNSE algorithm. We can see that zero method resulted in irregular distribution of the latent codes. However, linear and cyclical annealing showed a rather better regular distribution of the latent codes. And that explains why zero model produced the best perplexity on test set, but more grammatical mistakes in expert evaluation. We can expect that in case of the zero method, when sampling a code from the latent space where there is no density or a low density, there is a high chance to produce a grammatical mistake. Here we show samples from each model. The zero scheduling of variational autoencoder, which produced the best perplexity on test set, the constant model, which produces low number of unique sentences, the linear and cyclical annealing, which produced the best models in terms of grammatical correctness. Here are samples from RNN language model and sequence GAN. As we saw earlier, these models generate samples that capture statistics of the test set. In the conclusion, we created the dataset for text generation in Russian. We trained variational autoencoder and sequence GAN models using our new dataset. We experimented with 4 different scheduling methods for variational autoencoder, and we performed a comparison study using perplexity, statistical study, and human expert. Our results showed that variational autoencoder with zero schedule resulted in the best perplexity on test set, but with an irregular distribution of latent codes in the latent space. And the linear and cyclical annealing procedures resulted in better samples grammatically and a better result regular distribution of latent codes. RNN language model and sequence GAN samples have many grammatical mistakes, but statistics of the samples show that they are close to statistics of the test set. Mean and standard deviation of the number of tokens per sentence and the number of unique tokens. Thank you for your attention.